Oh, is this okay for you? Should I move it? Yeah. All right. I think it's approximately time to get started. Let me find the top hat. Let's see here. Top hat is always lost. We've got an update for you. Oh no, another time, thank you. How about never, Windows? All right. So, the top hat.
Really all it boils down to.
Yeah. The top hat is 6937. I'm giving them the code for the top hat. I will begin with a word of prayer. Dear Father, we thank you for this day again. I thank you for this class, for the break that's about to start. Just pray that you be glorified at what we do this day, Lord. In your name I pray, Lord Jesus. Amen. This is my son Benjamin. He's visiting. If you misbehave, he'll throw an airplane at you, I believe. That's what's on the schedule. So let's talk about force and momentum. And let's also throw impulse into the mix here. So last time, I explained that for a single point particle, the momentum is the mass times the velocity of the particle, right? And we saw that if we calculate dp dt, then that's d/dt of mv, which is m dv dt. And if we're talking about a single particle, that's the mass, mass times acceleration, obviously. And so that's equal to the net force, right? This is Newton's second law. So Newton's second law we can rewrite as dp dt equals to the net force. Another thing you can do with this, though, you notice, is we can integrate. Let's check this out. If we integrate from, say, time 1 to time 2, dp dt dt, well, that would be equal to the integral of the net force from time 1 to time 2, right? But what's the integral of a total derivative? It's just, I see you fashioned yourself a claw. Very nice. Ow! Why? So we have p of time 2 minus p of time 1 equals to the integral from t1 to t2 of the net force dt. And so this right here is a nice thing to know about. It says that the integral of the net force gives you the change in momentum for the mass, right? Now, the change in momentum is equal to the impulse. So impulse is change in momentum. All right? Sometimes the letter J is used for impulse. So in one dimension, so like for one-dimensional case, typically you see something like J is equal to the change in momentum. That's equal to the integral from t1 to t2 of just f of t dt, right? I mean, I suppose you could think of impulse as a vector as well. But, oh, here's an example. What if you had, so like here's force this way, and you have, here's a graph like that. Here's the force, graph of force versus time. what would the impulse delivered by this force be? So you have integral, I guess the question is over what time period, right? So just for the sake of discussion, let's say it's from time t1 to time t2, right? So you guys can tell me, like, conceptually, what is the impulse here equal to? Yeah. Area under the curve. Exactly. And what force would have a function like this? Like, physically speaking, can you think of any examples? Yeah. A push, right? How about like this? Let's try that again. Aw, man.
Sir, I think we need to find out the spring force.
Or that. Okay, there's some examples. So, here, I'll tell you what. I'll leave this with you. So something like, something hitting something, right? Classical example would be a hammer hitting a nail, right? This would be the impulse function, something like that. The mathematics is like, so the idealization of this is called the Dirac delta function. It's like a spike. So if you want to talk about something like a hammer hitting a nail at an instant, you use this function which goes to infinity at one point, and the area under it is just equal to 1. It's called the Dirac delta function. But maybe you'll talk about that. Don't lose my bullets.
I'll go get that.
Yeah, you better. All right. So there's an example. Another popular example is you've got some ball, all right, and it's going with, I don't know, 20 meters per second. All right, and the mass of the ball is, let's say, 3 kilograms. Well, that's all right, yeah. And then you've got Mr. Top Hat comes and he kicks the ball, right? So this is before. And then after the ball comes, he kicks it up here and it's seen flying away at, say 30 meters per second. Ow! Oh, my neck.
What a shot.
Dude.
Where's that bullet? I need it.
Not cool. I didn't shoot you in the neck.
You shoot me in the stomach.
Yeah, but you have like armor on. You gotta, come on.
Oh shoot.
What? Ow. Yowzers. All right, and so my picture is overly dramatic. I don't mean for this to be so far away that we have to consider gravity, like I was talking about last time. Let's suppose it's 30 degrees up like that, just for the sake of discussion. All right, and I do mean that it's 30 meters per second, like pretty much right after he kicks it. Okay. So, so here's the question: if the duration of him kicking the ball is 0.1 seconds during the kick, then find the average force applied by Mr. Top Hat. Do you guys understand the question? Guess I know how my son felt when he was playing airsoft with his brother and he didn't bother to cover his neck. Ooh, yeah, that's worse, isn't it? Although those are big. Airsoft's just a tiny little, well, that makes it worse, doesn't it? Okay, so the point here is to calculate the average force applied. What we do is we calculate, so here, another thing we could add to this list is that average force would just be change in momentum over change in time, right? If we're just interested in the average force, we don't need derivatives. We can just calculate the change in momentum or the change in time. So the mass of the ball is the same before and after, right? So let's see here. Let's get to it. P initial is 3 kilograms times 20 meters per second, comma 0. So we've got 60 kilogram meters per second, comma 0. What? Hey.
It was a trap.
Is that 22?
X to the 2 power.
No, that's x to the second power.
Oh, x to the second power equal x squared. Ah. I get it. EF. So the final momentum, so the mass of the ball is the same. So 3 kilograms. Can you guys help me out? What would the formula be for the velocity final? Gotta do some trigonometry here, right? So we've got like, looks like a minus 30 meters per second times what? Cos 30? And then 30 meters per second times the sine of 30. So by my calculations, the final momentum would be, can you guys help me out? I need to get a calculator.
77.942
77.942
kilograms per meter per second.
minus 77.942 kilogram meters per second. And the other one is 45, right? 45 kilogram meters per second. Are we good? Yes, no, maybe so. So there's the initial momentum, there's the final momentum. Now we can calculate the change in momentum. The change in momentum is final momentum minus initial momentum. It's a vector. And let's see, so we just subtract, right? So we've got minus 77.94, minus 60. I'm going to leave the units outside. And then I've got 0. No, my bad. 45 minus 0, so 45. All right, great. So then the average force of the Mr. Top Hat during the kick apparently is minus 137.94 and 45 divided by 0.1.
Hands up, Dad.
We've got kilogram meters per second times second squared. Interesting.
So is this one thing you make gun control?
Yeah, he should have better control of the gun, right? Let's see here.
Yeah,
137.
background check and,
9 point.
some training classes.
Yeah. 450 newtons. So there you go. That's the average force right there. Which is probably a bit much. I mean,
That is a very powerful.
what's the weight of a typical adult male in terms of newtons? 100 kilograms, let's say. So what's the weight of a 100 kilogram dude times 9.8 meters per second squared? That's what we got? 980 newtons.
Yes.
So this is like the weight
This is the force power.
of big dude.
It's gone.
Spring problem.
He's very
I didn't know you were.
Is he trying to be a stormtrooper?
This is going better than it went in Calculus 3. Calculus 3 completely destroyed my lecture, so it's relatively harmless. So yeah, well, I mean, this is borderline plausible. I don't know. What? You come right up to me. That's lame.
I can do it better. Want me to?
You shoot me from across the room at least. Otherwise, it's just, you know.
I got this. Move.
I'm going to lecture here now, though. So sorry. Oh, attendance sheet. There we go. Almost forgot. Any questions about this one example? So there's, hopefully there's at least a problem in the homework, you know, where I've given you some kind of before and after, and I asked you to calculate the net force. This gun does come with safety glasses, by the way. Yeah, I know. So another popular example is like you have a tennis ball. It comes in, it goes out, right? To calculate the average force on the tennis ball.
What it is.
Ow.
Sorry. I wasn't aiming for your head. I was aiming for your leg.
Well, that makes me feel much better. All right, Benjamin, I think that's enough.
He's about to put gun control measurements in place. Watch out.
You can just shoot Matthew instead.
Okay.
All right.
Hands up, Matthew. I know you're Matthew. Oh, what?
He's got the bullet. He's got the bullet.
Oh no. All right.
So do you just have a mini mercenary now? Like this?
Eh. All right. So. Let me start talking about collisions.
My dad is coming.
So, what is a collision? A collision usually involves, for us, typically we look at collisions of two masses, but in principle you can look at collisions involving more masses, right? I think current particle accelerators have something like two masses slamming together and then thousands of masses come out, and they've got these giant, you know, things the size of this building to detect all of the different particles going all the different ways. It gets really complicated. But for us, mostly, we're just thinking about two masses hitting each other. And so the idea is that, you know, we have masses slammed together, then go apart, all right? But the critical thing here is that the time that it takes is approximately zero. All right, like the before and the after for a collision, it's so fast, all right, that there's just simply not time for any force to be involved to change the momentum. So the key thing for a collision is that the momentum before is equal to the momentum afterwards. So, and I'm talking about total momentum. Are you distracting my class?
You want me to make you a stain on your pants or your belt.
2 times 6 equals to 12. 2 divided by 2, 12 divided by
12 divided by 2.
12 divided by 2 equals 6. Okay, yeah, I think I agree with that. We already seen this. This is a rerun. We already seen this. X to the power, second power equals x squared. We already. Oh, okay. Yeah. All right. Yeah.
Is that the vectors are equal or is that the magnitude?
The vectors are equal. Momentum is a vector quantity. It's conserved as a vector. Yeah. So, for example, example 3, I suppose. So suppose you've got car, all right, and maybe it's going, I don't know, 20 meters per second. And suppose that the mass of the car is, oh, let's say 2,000 kilograms. All right, and then you have a bike, all right, over here, and it's got, maybe it's going 50 meters per second. Yeah, it's really moving. It's like a Tesla or something. I don't know. Tesla make a bike? No. And suppose that the mass of the bike, including the rider, suppose it's got a fat baby on it. The baby's really fat. So let's say 200 kilograms. That way. Okay? And then they collide. And then you've got, you know, the car and the bike and the baby. And they're all together. Yeah, I'm sorry. The baby survived. It's not evil. So then the question is, what's this angle? And what's the velocity of the car baby system after the crash? All right? So initial momentum is, well, we got 2,000 kilograms, all right, times 20 meters per second, 0. That's the initial momentum of the car. The initial momentum of the bike is what? 200 kilograms times what? We got 0, comma 50 meters per second. All right? You guys with me so far? So the net momentum before, so we think about systems in these kind of problems, and so the assumption here is that whatever kind of friction and other things going on, they're irrelevant to the collision, because the collision, like these velocities, even though I draw the picture as if they're like really far apart, that's the velocity like right before they hit each other, all right? And then I'm interested in the velocity the instant right after. So there's no time for any forces to change this momentum or to change that. An interesting question to ask after the fact is like, how far would it slide given a particular coefficient of friction, right? We could figure that out. And okay, so what we got? The initial momentum is apparently, what's 20 times 2,000? 40,000? So we got 40,000. And the other one, give me what? What's 200 times 50? 20,000? 10,000? We got to vote for 10,000, vote for 20,000. We're going to go with 10,000? Yep. All right. And that's in kilogram meters per second. No shooting me. It hurts too much.
The ultimate gun control for safety. Always make sure
Where'd that go? Where'd it go?
Under the door.
Oh, really? Oh, wow. No, it went under the door. Did it really go under the door? Oh, wow. Matthew, help him. All right, so there's your initial momentum. What's the final momentum? So here we assume that mass is neither created nor destroyed, right? This is not one of those kinds of collisions. So that gives us 2,200 kilograms. That's the total mass, right? times the final velocity, which I'll just, call VFX, VFY. All right? So momentum is conserved in the collision, so all we have to do is equate these two. All right? So this, by conservation of momentum, is equal to 40,000, 10,000 kilogram meters per second, and solve for the velocity, right? This is the velocity, the final velocity. So the final velocity is equal to 40,000 divided by 2,200, comma 10,000 divided by 2,200, and we got meters per second there for units. So what does that work out to? Well, find out in a second here. What? All right, 40. All right, I got 18.18 meters per second, comma,
Where is that?
4.54 meters per second. All right, back here. So that's the final velocity. So what's theta and what's the speed? So we want, I'm going to put my calculator back into, I don't like radians, I want degrees. Let's see here, inverse tangent, 4.54 divided by 18.18. So I get theta equal to inverse tangent of 4.54 over 18.18. So I get about 14.02 degrees for the direction as I asked for it here. And what's the speed? What's the speed? So we take 18.18 squared plus 4.54 squared, and then we square root that thing, right? The speed, VF, would be 18.74 meters per second. All right? Any questions about this one? Yell me.
How do you open this? I need to reload it. How do you reload this? How do you open it?
It's still got bullets in there.
But how do you open it?
Well, you open it there.
Thank you.
Probably shouldn't help you. Don't shoot me again.
Okay.
All right. Let's see here.
I want this Nerf gun for my.
You want this Nerf gun?
Yeah.
Yeah, I don't think I want you to have that Nerf gun. Too dangerous for me.
Birthday.
For your birthday. All right.
At Christmas.
So I should mention, guys, there are two kinds of collisions. All right? Yeah, there are elastic collisions, and what's the other kind? Inelastic. It's annoying that they have such similar sounding names, but that's just what people say. So I blame other people. All right. Watch out, mister. What, no, what are you doing? Is that? Oh, fine. Okay. Ah!
That's what's going to happen.
Did that go through the paper?
How many sheets of paper can go through? Good job, Mr. President.
I think just get this paper out of the way and just get no, there's a hole.
There's a waterfall that I made last.
All right. So we have two types of collisions. You have elastic, and this means collision. We have the kinetic energy before equals the kinetic energy after. This is a elastic collision. We have the conservation of kinetic energy. In an inelastic collision, inelastic collision, we have that the kinetic energy before is not equal to the kinetic energy after. All right? Now, typically kinetic energy is lost in the collision. But that doesn't have to happen. It could be something like there's like some kind of explosion or something in the collision, right? And that could end up giving you more kinetic energy afterwards, right? But technically speaking, a elastic. Stop threatening the students. Go back.
I wouldn't point blank there.
He's probably still.
No.
Ah.
Hold it. Can we take it?
You have to go through the Stormtrooper Academy.
Well, you could
I can
consider.
borrow mine, too.
You should consider your behavior and what might happen.
Mine.
That's mine, actually. It's mine.
I got a Nerf gun at home. You don't want me to bring it next semester.
Ah, stop. All right. No. All right. Benjamin, I need that for now. It's too scary for me. No, that's my board. Nope. All right, Benjamin. So.
No.
All right. I will eventually. So the kinetic energy before and after is equal for an elastic collision. So
For the masterpiece.
example 4. Suppose you have two masses, all right? You have, let's say, MA, and over here you have MB. All right, this one initially has velocity v naught, and this one is initially at rest. All right, then they collide, and afterwards you have MA with VA, and you have MB with VB. Now I'm not trying to say Benjamin.
Give me that Nerf gun. Where is it?
Stop. Nope. Hey. Nope. We're done with the Nerf gun for now. All right. So now it's starting to feel like calculus. So it's okay. I've actually delivered important lecture facts already today. So whatever happens after this point, like, I'm okay. The point is, if we're talking about a collision here, right? In principle, I don't know for sure like what's going to happen afterwards. Now, I'm talking one-dimensionally, just to keep things simple here. Imagine a one-dimensional collision. Let's assume that we're talking about an elastic collision. So If you actually calculated the kinetic energy before and after, in my example 3, you'd find out that you had more kinetic energy before than after. All right, you could calculate that. So example 3 is actually an example of an inelastic collision, if we were to run the numbers on it. Let's assume that this is elastic. Let's work it out. Let's see what happens. So what's our initial momentum? And so this is one-dimensional, so we're going to use the convention that if it's going right, it's positive. If it's going left, it's negative. All right? And so I don't have to commit to, like when I write VA and VB here, I'm not saying necessarily that they're both going that direction. I'm just saying I'm defining positive velocity for those in that sense. So the initial momentum is ma. See, Benjamin, if you won't stop, I will not be able to let you come and visit again. But you'd like to visit again, right? So I suggest the rest of class, no more hitting me, okay? Someone gave you a starburst as payment? What?
The child was bribed as a mercenary.
So
Assassination plot.
PF is equal to
Don't remember I have a bullet in my hand.
MAVA plus MBVB. All right? Another thing I should mention, guys, is we can calculate momentum. I'm not sure this really matters for this problem, but something else to think about. For a single mass, kinetic energy is 1/2 mv squared, right? But since P is equal to mv, that makes V equal to what? P over V, right? P over M, rather. So another formula for kinetic energy is P squared over 2m. If you know the momentum, you can figure out the kinetic energy from the square of the momentum divided by twice the mass. Now, I don't know if I really need that for this problem. It just occurred to me I should tell you guys that. Okay.
If you wanted to say like the last one, like that example, that would be the way to calculate to show that it's not elastic, or is that purely?
We're going to assume elasticity of the collision here. All right? Assume it's elastic.
This is nothing.
So momentum is conserved. That's true whether it's elastic or inelastic. Momentum has to be conserved. So on the one hand, we have that this is equal to that. That's one thing we know. But we also know, so let me see here. Let me write that down. So we have MA VA plus MB VB is equal to MA V naught. Okay.
Oh.
No. All right, okay, very great. So on the other hand, we also know that 1/2 MAVA squared plus 1/2 MBVB squared, that's what? What did I just write down? I just wrote down the final kinetic energy, right? That is equal to 1/2
Your rubber bands in your office.
MAV naught squared. Yes, it's great. So what can we do here? Well, I mean, these are the equations that govern an elastic collision as I've set it up here. Can we figure out, like, what would be interesting to solve for would be, if we can't, I mean, can we solve for anything? Is there just one scenario here? Right? What has to happen?
I don't know, but it's one-dimensional, so isn't it just quite limiting what we can?
Well, I mean, the one-dimensionalness, you could think about it, it's kind of stupid, but when I say one-dimensional, we do allow I know this is hard to imagine, like the one mass could pass through the other one. That the mathematics has to allow for that. So you could think of it, it's nearly one-dimensional, so like, you know, maybe it's actually along a channel where there's enough room for like two balls and like the one could go past the other, or it could glancingly hit it or something. Anyway, there's probably a better analogy for it, but that's that's the mathematics of this, nevertheless, is what possibility, there is the possibility that the ball can pass through the other ball, mathematically speaking. Or of course it could just head-on bounce, right? Which is the more interesting thing, I think. So how do we solve these equations, right? Well, right, that's the question. So we're given V naught. We'd like to find whatever we can say about VA and VB. Okay? So can we say anything? Well, we can get rid of the fractions at least, right?
Yeah,
Multiply that by 2. All right, so I'm going to erase this. And
How much I erased from your math?
I've got MA VA squared plus MB VB squared equals to MA V naught squared. And I also have that MA VA plus MB VB equals to MA V naught. So one thing we can easily do here. So you don't want to come back ever again?
I do want to keep that.
All right. It's better. So how about this? We can easily solve both of these for V naught, right? Like V naught squared is what? See, on the one hand, it's VA squared, right? Plus MB over MA VB squared, right? You guys see that? But we can also take the second one and square it, right? So like this tells me that V naught, on the other hand, is equal to VA plus MB over MA times VB, right? So if I square that, I get V naught squared equals to what? VA squared plus MB over MA quantity squared VB squared. And if you think that's all there is, then I must send you to Dr. Sprano. And then he will yell at you and he will tell you this is bad algebra, right? Bad algebra. He won't yell at you, but in capital red letters on your paper, he will write bad algebra. In his mind, he's screaming at you. But he is nevertheless a gentle giant, so we're not bothered by this. All right, so we get twice MB over MA VA VB, right? Because we have the cross term in the squaring. And so if this is equal to that, what do you get? See, these two have to be equal because they're both equal to V naught squared, right? So we get then MB over MA VB squared is equal to 2MB over MA VA VB plus MB over MA quantity squared VB squared. Do you guys see what I did there? What have I canceled? So I'm saying V naught squared equals V naught squared, right? Yeah.
Should there be a flux between the VB squared and the MB over MA squared?
Maybe. Unfortunately, I can't read it from back here. I'll tell you when I get back up there. Are you talking about the rightmost board?
Yeah.
Did I miss a plus? I got a plus there.
No, I'm talking about the MB over MA squared over times VB squared.
Here?
Yeah.
I got plus there.
To the right, like that term. Is there not a plus sign between them? Or
I got 2 pluses. There's one here and here. Let me make them a different color. I'm hoping I'm hearing you. You're like, I'm colorblind. No. No, okay, good. But yes, there should be pluses. I mean, I'm squaring it out. It's the binomial squared. I get 3 terms, a squared plus 2ab plus b squared, so to speak. So then I get this equation here, right? And what does that tell us? What are the solutions? So either VB is equal to 0, right? That's one possibility. VB could be 0. What if VB is not 0? What do you get? Let's multiply this by m sub a. What do we got? We've got MB, VB is equal to 2 MB, VA, VB. Well, I'm going to divide by VB too, okay? So divide by VB and multiply by MA. We get MV VB plus 2MB VA plus MB squared over MA VB, which I could rewrite, if I haven't made a stupid mistake, I hope. All right, so I've got VB times what? VB times, let's say, MB minus MB squared over MA. That's my VB terms, and that's equal to 2MB VA. I'm starting to feel like I should do what?
Just divide both sides by MB minus MB squared over MA.
Divide both sides by what?
Wait, are we finding VB or VA?
I'm finding a relation between VB and VA at the moment. So this assumes, so to get down to here, I'm dividing by, supposing VB is not equal to 0 in this line here.
We just want to isolate either VB or VA.
I'm trying to find a relation between them. There should be some kind of, like,
You could get rid of MB,
to divide by MB.
and then you would have VA equals
VA equals what? Yeah.
jump over 2.
Junk over 2. I like that. So, goodness gracious, let me just, too much. 2 VA is equal to VB times 1 minus MB over MA, right? All right, so therefore, we have the equation VA is, like you said, we can write that 1/2. I guess we could write that MA minus MB over MA if we wanted, right? Times VB, right? Agree? All right, so then what does that tell? Let's try, see if we can't find more than just that. What was our, let's see if we can relate.
Dad,
What?
look at that.
Look at that. Are you trying to solve it? It's good. It's good. I think. I think we are done with the top of the board there. I'm trying. Okay, so what I want to do, if I have time. Do I have time? How much time do I have?
258.
It's what? 2:58. All right, we're gonna make it. We're gonna make it. We'll make it.
Dad, look.
We're gonna make it.
I underlined the thing.
We're gonna make it because I don't want to go through all this again. So, what is VB minus VA? All right, VB minus VA is VB minus 1/2 MA minus MB, supposing I haven't made a mistake, right? And I probably should have left it the other way, shouldn't I? But, oh well. VB? So what we got here?
VB minus VA equals 1 minus that being
Okay, so I probably should go back to 1 minus, probably easier to see that way. All right, so that's actually what? It's 1/2 plus, yeah, right, my bad. 1/2 of 1 plus MB over MA, right? VB? Yeah? Well, that's still not showing it to me yet. How about this? Oh, V naught. What's V naught equal to? I should use momentum conservation, guys. Sorry. So V naught is equal to, here, where was it? V naught is equal to VA plus MB over MA V naught, right? Not V naught, VB. So what's this equal to? Let's see here. So can you guys figure out how to, I want to change this to V naught. Can you see it? So I can trade this. I've got like 1/2 VB plus, sorry, it's not popping out at me. But this I can trade for 1/2 VB plus V naught minus VA.
Shouldn't it be 1/2 MB over MA times VB?
Say again?
Shouldn't that second term also be times 1/2?
Oh yeah. So that would make this times 1/2. Is that right? Is that right? And so then that would give me what? That would give me 1/2 VB minus VA is equal to 1/2 V naught, right? If I subtract it to the other side, is that right? Or am I? Yeah, I have 1/2 of VB minus VA over here. So if I subtract it over there, I've got 1/2 V minus VA equal 1/2 V naught. So therefore, VB minus VA is equal to V naught. That is the thing I was trying to derive. This is not the most efficient way through the algebra. I, for some reason, was distracted today. This could be simplified by 50%, but not by much more than that. There is a larger point here. In an elastic collision, here's the theorem. In an elastic collision, the relative velocity before the collision between the masses is equal to minus the relative velocity after the collision. So I might have done this wrong. Let's see, B minus A. Oh, no, I didn't do it. What the relative velocity before would be what? 0 minus V naught is the immediate relative velocity. What's the final relative velocity? VB minus VA. So you see we have, this is equal to minus 0 minus V naught. So here's the point of this. You can check if a one-dimensional collision is elastic by simply looking at the velocities of the masses before and after. If the velocity relative of the two before is not equal to minus the relative velocity of the two after, it's not an elastic collision. That's what this proves. And that is way, way easier to check than like actually computing kinetic energy. So anyway, my apologies for some distractions today. Yeah, you guys always like distraction.